height of a draft tube. Now, the maximum height of the draft tube in the turbine is affected by two considerations. The one is called flow separation. Now, you can see we have this shape of draft tube. Okay, so here the velocity is Vd, here the velocity is Vo. Now, further, this is at low pressure, this end is at low pressure, and this end is at higher pressure because here the pressure is uh, atmospheric or more than atmospheric. So, here we have the high pressure. Okay, now if we have a low height or less height of this draft tube, then what happens? If this draft tube has low height, now you can see to reduce this Vd, we have to increase the angle. We have to increase this angle. Okay, so initially from this angle to this angle, we have to increase if we want to decrease the height or length of the draft tube to maintain this Vd constant. Now, due to this, we have a pressure difference, low pressure and high pressure at inlet and outlet. So here again we have high pressure. Okay, so you can see in this case, as the flow moves towards the outlet, it may happen due to this large angle that flow separates from the sides of the draft tube. Flow separates from the walls of the draft tube. That is called flow separation. Now, due to this flow separation, there is a formation of eddies. Okay, and this eddies leads to energy loss. So we can say here, we can set the length of the draft tube in such a manner that there should not be the flow separation. So we have to avoid the flow separation. So this is the one factor which impact on, or you can say, which we have to consider while deciding the length of the draft tube. The second factor is the cavitation. So as you can see, at the inlet to the draft tube, the pressure is low, and that pressure is less than atmospheric, and that is by an amount equal to the height of the draft tube above the tail race level. Okay. Now, if you increase that height, then what happens? The pressure continuously goes on decreasing at the outlet. So a stage comes when at the outlet, or you can say when at the outlet or inlet to the draft tube, a stage comes, the pressure becomes less than, or you can say before less than becomes equal to vapor pressure of the liquid, that is the water. Now, when that pressure becomes equal to the vapor pressure of water, so at normal temperature, the evaporation, or you can say the boiling of water starts. Okay. Now, this boiling forms the bubbles at the room temperature. Now, when these bubbles reaches some region of increased pressure, so at that stage, at that very position, these bubble collapse. Okay. So these bubbles, so then you can say the bubbles are formed and move to high pressure region. So where these bubbles collapse, okay, so forms a high pressure wave. So this wave strike or collides to the surface and forms pits and cavities. Pits and cavities, or you can say, so that damage the surface where that wave strikes. So this phenomena we call as cavitation. So if we increase the length of the pipe beyond certain limit, then there is a danger of, or you can say there is a problem of cavitation. So again, we have to avoid this cavitation while selecting the height of the draft tube. So you can say these are the two factors which put limit on the height of the draft tube. So next is different types of draft tube. So you can see one is the conical draft tube, simple conical increased cross section draft tube. Now this is the spreading high cone draft tube. So this is the solid surface over here. This surface is the solid surface. Another one is spreading low cone draft tube. Next one is the elbow type draft tube. So elbow type are of two types depending upon the cross section at the outlet. So here you can see this is the elbow type draft tube with circular outlet, and this one is again the elbow type draft tube with rectangular outlet. So these are the different shapes or types of the draft tube. The next is different efficiencies. Efficiencies of Francis turbine. The first efficiency is the hydraulic efficiency, denoted by eta H. So its definition we already seen in the Pelton turbine. Okay, so here we can write the power produced per unit mass by the runner. Okay, so here we have angle alpha O equal to 90 degree at the outlet. So that gives us VWO equal to 0. So therefore, the power produced per unit mass we can write as VWI UI. And power input to the runner, again per unit mass is equal to GH. So we can write as hydraulic efficiency as VWI UI divided by GH. Now we can also write this efficiency into another form. Now we can also write this power produced. Now this power produced is equal to uh, the amount of energy utilized within the runner. Okay, or you can say this is the amount of energy transferred from one form to another form within the runner. So we can also write this as the energy supplied minus the waste energy divided by GH. So this is another formula for hydraulic efficiency. The second efficiency is volumetric efficiency. So that accounts the volumetric losses or water leakage or water loss. So this we noted by eta V. So eta V is QA divided by Q. So QA is actual discharge or actual quantity of water striking the blades or runner, and Q is total discharge or total quantity of water supplied. Okay, this is the total discharge. So this gives us the volumetric efficiency. The next one is mechanical efficiency. So this efficiency accounts all type of mechanical losses like bearing frictions, shaft or wind friction of the shaft. So like that, all losses comes under or accounts in mechanical efficiency. So it is noted by eta m. So eta m I can write as shaft output divided by runner output. Okay. Now further, runner output I can write as actual mass of water striking the blade multiplied by uh, runner output per unit mass. So this comes out to be equal to rho QA, the mass, multiplied by VWI UI. So I can write as mechanical efficiency is equal to shaft output divided by rho QA VWI UI. Then the last is the overall efficiency. So that is eta O. So this efficiency accounts all losses occur in the turbine, and it is the ratio of shaft output to the available power. So this I can write as shaft output divided by the available power is WQH or rho G QH. So Q is the total discharge and H is the net head. So now I can write this into another form equal to shaft output divided by rho QA VWI UI into QA divided by Q into VWI UI divided by GH. So this is equal to the mechanical efficiency into volumetric efficiency into hydraulic efficiency. So I can write eta O is equal to the product of other three efficiencies. Propositions for Francis turbine. The first is the ratio of B to D. Now this ratio we call as the ratio of width to diameter of the runner. Ratio of width of the runner to the diameter of the runner and denoted by N. For Francis turbine, this ranges from 0.04 to 0.5. Then the second is the ratio of tangential velocity ui to the quantity under root of 2gh. So ui divided by under root of 2gh, I write it as ku. So this is called speed ratio. For Francis turbine, the value of ku lies between 0.6 to 0.88. Then next is the ratio of flow component of velocity at inlet to the quantity under root of 2gh. So I write it as kf, and this is called flow ratio. And its value for Francis turbine lies between 0.12 to 0.35. The next is the formula for discharge through Francis turbine, that is Q equal to pi dB into Vf. So if we consider the blade thickness, so then this total discharge, this Q is on lower side. So I have to then multiply by a small k. Okay, so k is the factor when I have to consider the thickness of the runner blades. So k we call as the ratio of actual flow area to the total area. So if I want to write discharge at inlet to the turbine, inlet to the runner, you can say that is K pi di bi vi phi, and discharge at the outlet is K pi do bo vfo. So this is the discharge at the inlet to the runner. This is the discharge to the outlet to the runner. Okay, so these are the various proportions or propositions for Francis turbine. So this ends the theory part of Francis turbine. So next we start with the numerical. Thank you.